Hello and welcome to my AE2220 creative assignment number 2 about the intermediate axis theorem. So, today I'm going to start with a little story. So, whenever I'm at home, whenever I'm doing whatever, I like to play with my cell phone. It's very nice to toss, it has a very nice case, it's very impact resistant. So, whenever I toss my phone around, I start by rolling it, by rotating it around this axis. And when I do so, the phone simply spins in this axis all the way through the toss until I catch it again. Then I take my phone like this and I spin it like this. And when I do so, the phone spins in a perfect yaw, up, over, and down. However, whenever I spin it in the third axis, whenever I take it like this and pop it up in the air, I notice that it starts to rotate in multiple axes rather than just the roll and the yaw axes that I just shown. So today I wanted to take a little bit of time to try and explain why that is. So today I'm going to talk about a potential theory for why this happens called the intermediate axis theorem. I'm going to rotate a phone through 3 axes and record motion data, and then I'm going to attempt to use that to discover specific behavior of the phone during that coupled motion that I observed. So to start, there's a phenomena which likely is the cause of this effect. It was discovered in 1834 and confirmed during repair operations on Salyut 7, and is therefore nicknamed after one of the individuals who discovered this effect, a name unfortunately I don't think I should be saying. The effect appears in any object with 3 distinct axes, namely called principal axes. Usually these are 3 axes which are perpendicular to each other and align along the axes of symmetry of that object, are rotated around each axis. So when a rotation is started, the object will rotate only along the initial axis in a number of axes. However, whenever you rotate around that third axis, otherwise known as the parallel axis, the object will start to rotate in the other axes as well. So how exactly does that work? Why does it display this odd behavior? So when you consider the rotation of a 3D rigid body, the angular momentum is based on the moment of inertia in all 3 axes and the products of inertia, which result from cross products used to develop the angular acceleration of a rigid body. So whenever you differentiate those angular accelerations, you see that in the direction that the moment of inertia is not the highest or the lowest, the axis, i.e., the angular acceleration on that axis will spontaneously grow if any moments are applied that are not around that axis. In other words, an object spun around its intermediate axis, that third principal axis that isn't the highest or the lowest moment of inertia, it will be unstable. So under any displacement or any disturbance at all, it will magnify in the other axes of rotation and will ultimately spin 180 degrees. So to experiment with this behavior, I decided to take my cell phone and to toss it in the air in all 3 of these axes and see if I could use the onboard accelerometer to try and determine the specific rotational behavior of the phone in the air. So these 3 axes are going to be the yaw axis, which is an axis going which passes straight through the phone and goes through the just perpendicular to the surface. The roll axis, which is along the length of the phone, and then the pitch axis, which is along the short side of the phone. So whenever I did this experiment, I started with the yaw axis. When rotated around the yaw axis, the cell phone appears to be relatively constantly moving in a singular direction, in this case, W sub z, although you'll notice some interesting precessions in the other axes. These are likely as a result of some inconsistencies in how I started the rotation of the phone and in how the placement of the accelerometer might not be over the center of mass of the phone. So for the roll axis is very similar. This is another one of the primary principal axes, which was not the intermediate axis, so this is as expected. However, when we get to the pitch axis, we see something very interesting and unusual. So to begin, we notice that the phone does not maintain a constant pitch angular velocity like in the other situations, but rather it goes from a maximum to a minimum value. These rotation spikes are observed in the pitch and roll axes. The pitch axes instead of being at a constant setting, goes from a maximum and then goes down to a minimum. This suggests that the rotation is starting at a high level at the pitch axis, and then it will slow down and then speed up in the opposite direction. And looking at the other rotations in the other axes, we notice that the phone is likely starting a rotation in one way of the pitch axis, like this, and then as time passes, the other axes go unstable, so it starts to flip 180 degrees, and then it causes a rotation in the other axis, in the other direction over the pitch axis. This matches closely with behaviors that we predicted through the intermediate axis theorem and witnessed in the GIF of the tennis racket on that slide. So there's a couple of errors that I likely had. As I mentioned before, the rotations weren't perfect, especially in the roll axis where the moment of inertia were likely very, very small. I probably accidentally added additional moments, which caused extra precessions, which caused some of the variation that you had seen in those tests. So, however, ultimately, what we observed is that when the phone rotated normally through the roll and yaw axes, the pitch axis saw full reversal of direction, which suggests the same sort of unstable behavior which we had talked about earlier. So, of course, this is all well and good. This is very interesting to know how a phone behaves. However, we of course have to link this to aerospace. So obviously there is a direct effect. There's a direct link in the fact that this effect is discovered during the repair of a Soviet space station. The reason why it's discovered is because a lot of the hardware on that space station is held on using a wing nut, which is a very special type of nut with a couple of lobed ears, which has those three principal axes. So whenever it was rotated around the roll axes, that was actually the intermediate axis. So you saw that same unstable behavior that my phone demonstrated. However, the more obvious effect, the more relevant effect to aerospace is in satellite guidance and control. So a satellite, when in orbit, is very rectangular and has long, thin solar panels. This, of course, lends us to having three principal axes and two, which are both the minimum and the maximum moment of inertia. And as a result of that, whenever you rotate the satellite around that intermediate axis, you're still going to observe that same sort of instability that you might have seen in my phone, even if it might be somewhat mellowed out by the weight of the satellite. So the implication of this is whenever a satellite is in orbit and performing guidance and control maneuvers, there's going to be a certain sort of extra instability and extra moments that you have to take care of, which will likely use more fuel if rotated in that direction. Therefore, communication satellites should probably rotate around the other axes rather than the intermediate axis. So with all of that said, that should be all from me for tonight. See you guys later.